this video is going to talk about two things, Dalton's law of partial pressures as well as mole fractions. Both of those things are related and they are often used in the same question. And so Dalton's law of partial pressures is kind of my favorite law. It's just a little bit silly. So Dalton's law of partial pressures says that if you have a container that has a bunch of gases in it, you're going to be able to find the total pressure in the container by taking all the partial pressures of the individual gases and adding them all together. And so that's kind of, for most people, it's an obvious thought, but there is a law that talks about that. And if you're looking for the actual equation, here it is. So if you have a mixture of three gases, you'll take the individual partial pressure of each of those three gases, add them all together, and you're going to get the total pressure in the container. Now you can use the ideal gas law to calculate the individual pressures if you would like. And then if you wanted to find the total pressure rather than using Dalton's law, you could also add the moles together and still use Pfiffner. Either way, you could get the total pressure in the container. It really just depends on what information you're given in the question. And remember that because we're dealing with ideal gases for now, we are following the kinetic molecular theory that says that individual gas particles, the volume of them, is not really as important, and the forces among them are also not important. So we're going to ignore the nature of the individual gas particles, which we're going to ignore until the very end of the unit when we talk about real gases and we talk about the van der Waals equation. But until then, these assumptions are okay to make. Alright, so if we look at this particular problem, and we're going to use Dalton's law to figure this out. So when you have a mixture of helium and oxygen, and that's often used in scuba diving tanks, and it helps to prevent the bends. So for a particular dive, 46 liters of oxygen gas and 12 liters of helium are pumped into a 5-liter tank. Both gases are added to the tank at 1 atmosphere of pressure at 25 degrees Celsius. The question is being asked to determine the partial pressure for gases, for both gases, and the total pressure of the all the gases in the tank at 25 degrees. So we're going to be using Pfiffner. And we're going to start by finding the moles of each gas individually. So before they were pumped into that 5-liter tank, just how many moles of gas we had. In order to do that, we're going to use the ideal gas law. So it says here that they were at 1 atmosphere initially. So 1. It says we have 46 liters of oxygen, so let's use that one first. We're finding the moles of oxygen. R is the universal gas constant. And it says we're at 25 degrees, which is 298 Kelvin. And before I do the math, I'm just going to quickly set up the other problem to solve for the moles of helium. So we have 1 atmosphere, and in the question it says we have 12 liters of helium. We're now trying to find the moles of helium. And we're still at 298 Kelvin. So if we do this math, we get that the partial pressure of oxygen gas is 1.9 moles, and the partial pressure of helium is 0.49 moles. So now we can use Dalton's law, or the idea of Dalton's law, and we can find the partial pressure of each gas. So I'm going to use Pfiffner to do that again. Now there are a couple other ways to do this, but I'm just going to use Pfiffner again. And so we are trying to find the partial pressure of the oxygen gas in the tank. And in the question it says that the scuba diving tank is pumped into a 5-liter tank. So our new volume here of the tank is 5 liters. Moles is the one we just found. So 1.9, 0.08206. And the question doesn't say anything about the temperature changing, so we're going to use 298 again. And I'm going to set up the exact same question to find this. And we're still in that 5-liter tank. 0.08206. And we're still 298. Oh, I did not mean nitrogen, I meant helium over here. And if we do a little math, you get that the partial pressure of the oxygen is 9.2 atmospheres. And in that scuba diving tank, the partial pressure of helium is 2.4 atmospheres. So that's the question, that's answer to the question that's being asked of the partial pressures. Now the second part of that question asks for the total pressure in the container. And so Dalton's law says that the total pressure in the container is the partial pressure of the oxygen gas plus the partial pressure of the helium gas. So using Dalton's law, I can find that the total pressure in the tank is 11.6 atmospheres. So again, we combined Pivner a couple times and Dalton's law to find the partial pressures of the gases and the total pressure in the container. The second thing we're going to talk about in this video is mole fraction. So mole fraction is the ratio of the number of moles of a given component in a mixture to the total number of moles in the mixture. And so it's really just a fraction, part over whole. And so you can either use the moles as your part over the whole, or you can use partial pressures. And so this X symbol here, that's the symbol for mole fraction. And you will notice on your reference sheet, this equation is given, but then it also takes it and rearranges it, and it also has this equation on there. And so this equation allows you to find the partial pressure of any container if you have the mole fraction. And so you would take the mole fraction times the total pressure, and you get the partial pressure, which is just a rearrangement of this part of the equation. We're going to do a couple examples of using this particular equation. And this is on your reference sheet, so it's not something you ever need to memorize, but it is something that's used quite a bit. So again, mole fraction is directly related to pressures as the equation showed, and so if a gas is responsible for 25% of the pressure, it's going to be responsible for 25% of the moles in the container. So here's the question, here's the example we're going to work on. What is the total pressure in a container if 52.5 grams of nitrogen and 33.7 grams of oxygen are mixed, and the partial pressure of nitrogen is found to be 2.6? So we're looking for the total pressure in the container, and then the second question is asking for the partial pressure of oxygen in this container. So I know if we tackle the first question first, we're dealing with nitrogen. And so I know from the last slide that the partial pressure of nitrogen gas is equal to the mole fraction of nitrogen times the total pressure in the container. So I know the partial pressure of nitrogen gas. I don't know the total pressure, that's what we're trying to find, which means I need to first figure out this, the mole fraction. And so the mole fraction of nitrogen is going to be the moles of nitrogen gas over the total moles in the container. So we got to do a little stoichiometry to figure out both of those numbers. And so 52.5 grams of nitrogen gas, we're trying to find moles of nitrogen gas. So we're going to put 1 on the bottom, and on the bottom of this one we'll put 28.02. You get 1.87. We do a similar calculation to find the moles of oxygen gas, so 33.7 over 32. You get 1.05. If I add these two together, that will give you the total moles in the container, which is 2.92 moles. Well, now we have the partial moles and we have the total moles, and so we can use this equation up here to find the mole fraction. So the mole fraction of nitrogen is going to be the moles of nitrogen divided by the total moles in the container. And if we do that math, we get 0.640. And so now we can go back to that initial equation, and we have our mole fraction, and we have our partial pressure. And so using those two numbers and this equation up at the top, we can figure out what the total pressure is in the container. So the partial pressure, 2.6, is equal to the mole fraction times the total pressure in the container. And so the total pressure in this particular container is going to be 4.1 atmospheres. And this container is a mixture of nitrogen and oxygen. So according to Dalton's law of partial pressures, the total pressure in the container is equal to the partial pressure of nitrogen gas plus the partial pressure of oxygen gas. And so we can use Dalton's law to figure out the partial pressure of oxygen, which is the second part of this question. And so the total pressure that we just found is equal to the partial pressure of nitrogen gas that the question gives us. Oh, that should be a plus sign. And then just doing some subtraction, we get that the partial pressure of oxygen in this particular container is 1.5 atmospheres. And so there is the second answer to that question. Okay, I'm going to do one more question. It's pretty similar, but just so you can see another example. So suppose you have prepared a mixture of 22 grams of propane and 11 grams of isobutane. This mixture is then forced into a can until the total pressure is 1.5 atmospheres. What are the partial pressures of propane and isobutane? So I'm going to first take my grams and I'm going to convert them to moles because I know I'm going to have to use the mole fraction equation at some point. So if I have 22 grams of C3H8, and I'm just going to do some basic stoichiometry, and I converted that to 0.499 moles. And I'm going to do the same for the 11 grams of isobutane. And when you do that stoichiometry, you get 0.189 moles. And I will be needing the total moles at some point because I'm going to use that mole fraction equation. So add those together. Alright, so if I try to find the moles of propane first, so if I use that mole fraction equation that we did a couple slides ago, so the partial pressure of your propane is equal to the mole fraction of propane times the total pressure in the container. So my mole fraction is the moles of propane over the total moles, and I'm going to multiply it by the total pressure. So if we do this calculation, you end up getting that the partial pressure of the propane is 1.1 atmospheres. And then we can just use Dalton's law of partial pressures, that the total pressure in the container is going to be the pressure of the propane plus the pressure of the isobutane. And so the total pressure in the container is 1.5. 1.1 is what we just found. So the partial pressure of the isobutane is equal to 0.4 atmospheres. So there's one answer, and there's the other. So that is mole fraction and Dalton's law of partial pressures.